In this video, we're going to discuss gyroscopic motion and we're going to look at the effects of gyroscopic torques. Now, before we can understand gyroscopic motion, it's important to understand how we can represent rotational quantities, such as angular velocity, angular momentum, and torque, in terms of vectors. Now, the way that we do that is by using something called the right-hand rule. And on the screen here, we have a diagram from lumenlearning.com. And on the left-hand side, we see a rotating disc. Now, viewed from the top, this rotating disc is rotating anti-clockwise. But what we see is the direction of the angular velocity vector and the direction of the angular momentum vector is directly upwards. Now, the way that we determine the direction is by using the right-hand rule. So on the right-hand side of that diagram, we have pictured a hand, and the fingers represent the direction of motion. Now note that this is the fingers of the right hand, so if you imagine your fingers travelling in an anti-clockwise direction, then the thumb indicates the direction of the vector, so in this case, directly upwards. Now this can also work in the opposite bias, so if we know the direction of the vector, directly upwards, then the fingers would represent the direction of motion, or the direction of motion that vector is intending to cause. And these are some of the principles that come into play when we look at gyroscopic motion. So let's apply this to an example. And for the purpose of each of our examples, we're going to be looking at situations where we have two angular velocities acting mutually perpendicular to each other, or at right angles to each other. And what we're going to do is determine the effects in terms of torque as a result of those two angular velocities. Now all of this will become a bit more apparent as we work through the example. So what we have in the top left-hand corner is a picture of a boat or a ship, and on top of the boat we have a motor that's most likely being used to propel that boat forwards. Now we've been given some information. We've got the rotational speed of the rotor within the motor, that's the rotating component. We have the effective mass of that rotor, and we also have the radius of gyration for the rotor. We've been given some additional information. It tells us that the boat is going to pitch its bow at 0.015 radians per second. Now, although that's technical jargon, what it really means is the front of the boat is going to pitch downwards at 0.015 rads per second. So if we was to add this to our diagram, we would have a downwards angular velocity for the front of the boat of 0.015 rads per second. Now, as mentioned, what we're going to be doing is we're going to be calculating the gyroscopic torque acting on this boat when two perpendicular angular velocities are at play, and we have our formula in the top right-hand corner. The reason we have two angular velocities perpendicular to each other is because the motor of our boat is rotating, and its axis of rotation is shown on the diagram. Let's call that, for argument's sake, the x-axis. Now, in addition to that, we have the bow of the boat pitching downwards. Now, the axis for that rotation is either going to be into or out of the page. So if we can picture this, we have an arrow coming out of the page, and that would represent the y-axis on our Cartesian axis. We could also picture that as being into the page, which is represented by the symbol a circle with a cross through. But what we can see clearly here is that our x and y axis for each of those rotations are perpendicular to each other. So now let's determine the magnitude of each of those rotations. Now the first thing that you've probably noticed is that the angular velocity for our rotor is not currently in SI units. We have 4500 RPM. Now, in order to turn that into an angular velocity in SI units, and we've mentioned there that the axis of rotation of the rotor is being represented as our x-axis, we need to do a conversion. And the way that we convert RPM, or revolutions every minute, into radians every second is first of all by multiplying by the number of radians in a revolution, and then dividing by the number of seconds in a minute. We've seen that conversion factor previously. So our angular rotation then with the x-axis as the axis of rotation equals 471.24. And that's radians per second. Now, if we refer to our formula, we need two more variables. We need to know I, the moment of inertia, and that's going to be the moment of inertia of our rotor. The simplest way to think of this is that the second angular velocity, or the angular velocity in the y direction, is acting on the angular velocity in the first direction, or with the x-axis as its axis of rotation. So I for our rotor then is mk squared. Again, we've seen this formula previously. When we have an effective mass and a radius of gyration, the moment of inertia is just mk squared. Therefore, plugging in our numbers, we have 650 times 0.55 squared, which equals 196.625. Kilogram metre squared. So the last thing that we need to do in order to calculate our torque is include the angular velocity with the y-axis as its rotation. Now the question specifies that as 0.015 and it's already in radians per second. So we have the gyroscopic torque equals I 196.625 times omega in the x direction 471.24 times omega in the y direction 0.015, giving us a torque equal to 1390 Newton meters, accurate to the nearest whole number. So we know the magnitude of our gyroscopic torque, but what we don't yet know is what impact this is going to have on the boat. And this is where we need to apply the right-hand rule. So in order to determine the impact that the gyroscopic torque is going to have on our boat, we first need to specify the direction of rotation of the rotor. So let's assume in this instance that the motor was turning clockwise. So if we refer to our diagram, viewed from the back, our rotor is turning clockwise. So viewed from the side, it's coming out of the page like so. The reason this is important is because if we apply our right-hand rule, we can imagine our fingers moving in the clockwise direction around the outside of the motor. Then our fingers would be in this direction, meaning our thumb would be acting forwards like so. What this means is the direction of the angular velocity and the angular momentum vector for the motor is in the x direction, or forwards. But when we pitch the bow, the direction of that vector is going to change, and it's going to begin pointing downwards at a slight angle. Now that angle is going to change the further the boat pitches. But the important thing here is the direction of our angular momentum vector has changed. So next we need to consider what's caused this change in our angular momentum vector. And if we think of the context of the boat, then in all likelihood this would have been done using a rudder or something similar. And the way that we evaluate the torque from this rudder is by connecting the original angular momentum vector to the new angular momentum vector. And I'll demonstrate this on the diagram. We have a torque acting downwards, which represents the torque applied by the rudder. But it's important to note at this stage that the torque we're interested in is the gyroscopic torque that's going to have an impact on the boat as a whole. Now the gyroscopic reaction torque actually opposes the torque that created the change in the angular momentum vector. So our gyroscopic reaction torque actually acts in this direction, T subscript R. Now using our right-hand rule, we can determine what impact this is going to have on the boat, because with our thumb pointing upwards, and recall this is the thumb on our right hand, our fingers are going to be travelling outwards like so. Therefore, the reaction torque is causing a motion into the page, like so. So the impact this is going to have on the boat is to cause it to turn or yaw to the left. So again, if we refer to our original diagram, the front of the boat is going to turn or yaw left and into the page, like so. So just to recap, the rotor is turning clockwise when the boat is viewed from the back. And this caused an angular momentum vector in the forward direction. However, when the boat pitched downwards, the angular momentum vector changed and we ended up with a new angular momentum vector. We said that the thing causing that change in the angular momentum vector was a torque applied by a rudder or similar. But as we know from Newton's laws, every action has an equal and opposite reaction. So the torque that we apply is opposed by a reaction torque, TR. And it's that reaction torque that's going to impact the motion of the boat. So we used our right hand rule with our right thumb acting upwards, and therefore our right fingers indicating the direction of motion. And in this instance, the direction of motion was into the page. Now relating that back to our boat, into the page represented a turning or yawing to the left. Let's take a look at a second example to reinforce some of these points. In this second example, we have a motorbike, and the motorbike is going to be travelling around a bend. I've sketched on the radius of the bend, and here we have the two wheels of the motorcycle. I've also provided a second sketch of one of the wheels of the motorcycle, which will be useful in determining directions of rotation and so on. So what we can see here, once again, is that we have two angular velocities acting. We have the angular velocity of each of the wheel, and this would be their axis of rotation. If we look at the second sketch of our wheel, then that would be into the page, like so. And our second axis of rotation would be at the centre of our larger circle, and with reference to our larger diagram, the axis of rotation would be into the page, but with reference to our second diagram, the axis of rotation would be downwards. It does take a little bit of visualisation here, but once again we can apply our right hand rule, because if we imagine our bike being propelled forwards, then our wheels are going to be rotating forwards. And if we were to wrap our fingers around the direction of motion, then our thumb would be pointing into the page on this secondary diagram here. Now, if we were to repeat that for our second motion, if we imagine our fingers moving in the direction of motion here, once again, our thumb would be pointing into the page. However, if we imagine on our secondary diagram, as the wheel banks to the right, our fingers would be rotating out of the page. And if our fingers are rotating out of the page, then our thumb would be pointing downwards. But what we can see here, although we have two different views of the diagram, is those two angular velocities are perpendicular to each other. Let's, for argument's sake, specify that the angular velocity of the wheels has the axis of rotation of the x direction, and the angular velocity of the bend has the axis of rotation of the y direction. So next, we need to calculate some parameters, and we know that we need the moment of inertia for the wheels. So I equals mk squared. We have the mass of our wheels as 35 kilograms. And we have the radius of gyration of 0.22, giving us a moment of inertia equal to 1.694 kilogram metre squared. But it is important to note that that value is for each wheel. Therefore, the total moment of inertia is going to be double. So the total is going to be 3.388 kilogram metre squared, and that's taking both wheels into consideration. Next, we have the linear velocity of the bike. Now, if we know the linear velocity of the bike, then we know that that's also going to be the linear velocity at the outside of each wheel, because each wheel is in contact with the surface. Therefore, the linear velocity is going to be equal to the linear velocity at the outside of each wheel. Let's convert that linear velocity first into meters per second. So at the moment we have a velocity equal to 55 kilometers per hour. Well, 55 kilometers into meters is 55,000 meters. We times by 1,000 to get from kilometers to meters. But we don't want the number of meters travelled in an hour, we want the number of meters travelled in a second. So we need to divide by the number of seconds in an hour, which is 3600. 3600 is the number of seconds in a minute, 60, times the number of minutes in an hour, also 60. 60 times 60 is 3600. Again, we've seen earlier tutorials on how to do these conversions, but that gives us a linear velocity in meters per second equal to 15.28 meters per second. But we don't want the linear velocity, we want the angular velocity. So we can use the formula that connects linear and angular velocity, V equals r omega. But as we want the angular velocity of the wheel, we're going to need to take the velocity in meters per second and divide it by the radius of our wheel. Take care here, it's the radius of the wheel, not the radius of gyration. So we get our 15.28, we divide by the radius of the wheel, which is 0.28, and we get an angular velocity in our x direction, as we specified it, equal to 54.56 rads per second. Next, we can calculate our angular velocity in the y direction. Again, using the same formula of v equals r omega, except this time our velocity is 15.28, the same as previously, but our radius is the radius of the bend. What we're considering here is the tangential velocity here, and the radius is the radius back to the centre of our circle. We know that the radius of the bend is 35 meters, giving us an angular velocity y equal to 0.4365. So the final step then is to plug that into our torque equation, and we get T equals I, and it's the combined I of 3.388 times omega x, 54.56, times omega y, 0.4365, giving us a torque equal to 80.7 Newton meters. Okay, so we have the magnitude of our torque, but what's its impact? So if we think right back to the first principle of the right-hand rule, we said that we would wrap our fingers in the direction of rotation of motion. So on our wheel, that's clockwise as viewed from the inside of the circle. And in doing so, the direction of the vector is the direction of our thumb, which was into the page like so. We can relate that to our second diagram. We have the angular velocity of the wheel, and the direction, therefore, is the direction of our thumb, like so. So if we have the direction of the angular momentum of the wheel like so, then as we go round that bend, the direction's going to change. So further along the bend, the direction is going to be here. The next step in our process is to determine what caused that change in the angular momentum vector. Now in this case, it will be a torque applied by the rider. So as the rider turns the handlebars, it applies a torque, T. But as we mentioned in the previous example, it's the reaction to that torque, or the gyroscopic reaction torque, that's going to impact on the bike and the rider. So T subscript R. And the reaction torque opposes the torque that was applied in order to cause that change in the angular momentum vector. So once again, we can apply our right-hand rule, because with our thumb pointing in the direction of the gyroscopic reaction torque, our fingers will be in this direction like so. Now if we relate this to our rider, we have a reaction torque in this direction here, TR. Therefore the impact of that reaction torque is to try to tip the rider outwards, or outwards from the radius of the bend. Now if we think what cyclists and motorcyclists do when they go round a bend, is they lean into the corner. And the reason they lean into the corner is to counteract this gyroscopic reaction torque and to prevent themselves from tipping outwards towards the outside of the bend. We can also check this with our second sketch, because with our thumb pointing backwards or opposing the direction of travel, our fingers rotate round like so. So once again, we can see that our fingers are indicating a motion outwards towards the outside of the circle, or towards the outside of the radius of the bend. So we can see that practically using the right-hand rule, but we can also visualize the rider leaning into the bend to counteract that motion. So just to summarize, in this example, we used the right-hand rule to determine the direction of our original angular momentum vector, based on the direction of rotation of the wheel. We then considered the impact that the rider applying a torque, or a turning force, had on the angular momentum vector. Next, we considered the fact that every action has an equal and opposite reaction, so we said the torque applied by the rider must have an equal and opposite reaction. And it's that gyroscopic reaction torque that's going to have an effect on our rider and on our motorcycle. By applying our right-hand rule once again, we saw that that gyroscopic torque was tending to tip the rider to the outside of the radius of the bend.